Last speaker is Giuseppe Pipoli from the University of l'Aquila. His title is Vanishing theorems for minimal stable hypersurface. Please start.
Okay, good afternoon, everybody. It's a real pleasure for me to talk with you, even if not in person, but unfortunately I'm not able to come. And thanks a lot to Professor Koike for the invitation. And I would like also to apologize to all the speakers because the program was very interesting, but the jet lag with Italy is too much. And so I wasn't able to attend the previous talk. Can you hear me well, right?
Oh, yes,
Can you hear
please
me?
start.
Okay, thank you. So let's start. Okay. So the main argument is some property of minimal stable hypersurfaces in a Riemannian manifold. Okay. So I would like to start very briefly introducing some notation, let's say. And so we start from any Riemannian manifold, any hypersurface, and we denote by capital A the second fundamental form, defined as usual as the normal component of the Levi-Civita in the ambient space. It's very well known that this tensor capital A is symmetric, so it is diagonalizable, and the eigenvalues are called principal curvature. Okay, so the main object today is the sum of this principal curvature, which is called mean curvature. Of course, once you define the mean curvature, the easiest thing that you can ask is that this mean curvature vanish. And so in this case, when the curvature vanish in any point, the hypersurface called minimal. They are very, very important for a lot of application in geometry, but probably one of the most important reasons for studying such a hypersurface that they are critical points for the volume functional. Okay, I can compute the volume, the variation of volume of a hypersurface when I define the surface, and this surface is critical if and only if it's minimal. Okay. Now, once you have critical points, you can ask for minimum, maximum. Okay. And so, roughly speaking, a stable minimal hypersurface is a sort of minimum value for the volume functional. And if you write down the second variation of the area, you end up with this equivalent condition for stability. So for any test smooth with compass support test function, we have a relation like this. Integrating by part, we can arrive to an expression like this, which means since this expression also for any test function, it means that this capital J, this operator capital J called Jacobi operator is non-negative. Okay, so it's a special class of minimal hypersurfaces, but they are very important. So let's see some very first easy consequences of stability. So when M is closed, we can take closed means compact without boundary. We can take as test function any constant function, for example 1. Okay, and so the previous here we read 0 because the gradient of a constant function is 0. So stability means under this hypothesis, stability is equivalent to this condition, point by point, where this is the norm of the second fundamental form, and this one is the Ricci tensor in the ambient space computed in the unit normal of the hypersurface. Okay, So this one is for sure non-negative, let's say. This one, we don't know if it is a sign. So supposing that the Ricci has a sign, it means that stable hypersurfaces are trivial. So they are totally geodesic in particular. And another interesting fact is that if the Ricci is strictly positive, so we are, for example, in the sphere, any space of strictly positive sectional curvature, then this condition is impossible, of course, because this one is not negative, this one is strictly positive. So it means, for example, the round sphere has no closed stable minimal hypersurfaces. Okay. A very important problem in this setting is the so-called Bernstein problem. The ambient space now is the Euclidean one, and we know that hyperplane are minimal, and it's easy to prove that they are stable too. So people starting from Bernstein try to understand if they are the only stable minimal hypersurface in the Euclidean space. And what this is very interesting, the answer depends on the dimension. So a classical result says that this Bernstein conjecture was true. So the only minimal stable complete, of course, hypersurfaces or R3 are hyperplane. And very classically, we know that it was false for n bigger or equal than 7 by contrasample, famous contrasample by Bombieri, De Giorgi, Giusti. Now, in recent year, we have a series of spectacular results who prove Bernstein conjecture in another dimension 3 by Chodos and Ciauli, and with different technique by Catino, Mastrilli, and Roncoroni. N equal to 4 again, Ciauli, Chotos, collaborator, and very recently Laurent Mazet, the case n equal to 5, and the case n equal to 6 is still open. Okay, so you can see many mathematicians that contribute to this nice problem. In particular, you can see that there are more than 40 years passed for a new development. Okay, for passing from n to equal to 2 to n equal to 3, we needed a lot of time. But what happens in the meanwhile? Of course, the Bernstein conjecture was a central problem in the field. People continue to think about it, and in this period, 1981, 2021, some other partial results arrive, in particular weaker result, which gives them some topological obstruction. And in this sense, I would like to mention this very nice result by Tanno. And so the special case p equal to 1 is due by Palmer, and the theorem by Tanno says the following: we have in the Euclidean space of dimension with n smaller than 4 an oriented complete stable minimal hypersurface. Pick a p integer between 0 and n, then there are no non-trivial harmonic LP form on M. So the space of harmonic P form, integrable harmonic P form, is 0, is trivial. And this one gives some topological information at infinity. For example, the case P equal to 1 was studied by Palmer because it's related to the number of ends of the hypersurface. Okay, to be honest, today this result is trivial because we had this huge development in the Bernstein conjecture. So under this hypothesis, the dimensional hypothesis, we know that M is an hyperplane, but we know today. At that time it was not known, and And moreover, me and my collaborator, I forgot to mention that the original part of this talk is a collaboration with my colleague Francesco Bei from Sapienza in Rome. And me and Francesco, we like very much the strategy of the proof of this result by Tanno. And we were curious, at the beginning of this project, we were curious to what happens in Riemannian manifold. So what happens if we change the Euclidean space with a curved Riemannian manifold? Is it possible to take not so restrictive hypothesis on the dimension? Okay. With this in mind, the first result is again in Tanno paper, who study completely stable minimal surface in Riemannian space, but just for one form. Okay. So the condition about the curvature of the ambient space is that is B Ricci is non-negative, where the B Ricci is the following modification of Ricci tensor. So B Ricci in x and y is Ricci xx plus Ricci yy minus the sectional curvature of the plane spanned by x and y. Okay. So Tanno proved that if the B Ricci of the ambient is non-negative, then any harmonic integrable one form, the length of any such form is constant. Moreover, if the volume of the minimally per surface is infinite, then we have, as before, a vanishing of this group, because any such form is trivial. Okay, but once again, me and my colleague Francesco Bei, we were interested in trying to do similar result for the other exponent p. Okay, not only one. And okay, we will see. So there are some other related results in literature. For example, Zhu study the similar problem in the round sphere, or in five-dimensional Riemannian manifold with a very strong pinching. Today, also this result is how to say, no, that one today we know that this result is completely empty, so there are no examples here, because there is this strong result of Catino, Mastroli, and Roncoroni, who say that in a Riemannian manifold with dimension small enough, with non-negative sectional curvature, a uniformly positive Ricci curvature, exactly it's the case of the sphere, there are no complete orientable minimally per surface at all. First, at the beginning of my talk, we saw that, for example, in the sphere, it's not possible to have a closed minimal stable hypersurface. They prove that if the dimension is small enough, there are not at all, not closed, not compact, and no stable minimal hypersurface at all. And so, but once again, we like the style of the proof of this result. So keep in mind to try to generalize this nice result by Tanno, as I say some minutes ago. Me and my collaborator, we try to give a unified approach to this kind of proof. So we try to give at the same time a unified approach and generalize this kind of proof as much as possible, no? as much as possible. So our setting is the following. So first of all, we state a general result which at first view has nothing to do with minimal hypersurfaces. It's a general result that has his own interest. And then in the final part of the talk, we will apply this general result to the problem of a minimal stable hypersurface. Okay, so the ingredients for the general results are the following: a Riemannian manifold, a Clifford modulus on it. Okay, I don't want to enter in details. A Clifford algebra is algebraic stuff, but what you have to think in mind is this Clifford modulus is how to say, the most abstract setting where we have a Dirac operator, so a way to compute derivatives in some sense. Okay, so if you are not familiar with this Clifford module, no, it's not important. No? You have to think that we have a way called Dirac operator to derive object, and associated to the Dirac operator, there's its Laplacian, which is just the decompose with itself. Okay, so and another important ingredient is this Weissenbruch formula, which says that the Dirac Laplacian is the composition of 2 times the Levi-Civita connection plus a remainder, and this remainder is linear. Okay, so here that's our general result. So in the above setting, suppose that our Riemannian manifold is complete, and there exists a function Q such that the remainder in the Weissenbruch formula plus Q as a sign, and then the Dirac Laplacian minus Q as a sign in this weak formula. This one is the L2 product, so it is the integral of the product of the 2 elements. Okay. Okay, so we take our integrable, taking an S which is integrable and harmonic. Harmonic in this set means that Laplacian is 0, and so in particular the Dirac is the derivation through the Dirac is 0. So this is L2 and this is harmonic object at constant length. And then easily, once you have this first conclusion, you can also have very easily the second conclusion, that is, if the volume of the manifold is infinite, then these are harmonic L2 object has to vanish. Okay. Are there any questions about the statement before going into the proof? Okay, so the idea, okay, as I told you, this result is independent, but of course inspired by the theory of because we aim to apply it to minimal stable hypersurfaces. So this condition looks like stability, and if we subtract the Q, we have to add somewhere else. Okay, that's the reason for such hypothesis. Okay. Let's give a sketch of the proof. So we start by an exhaustion of n by relatively compact set, and as usual, for any n, pick a cutoff function, so bounded, which is equal to 1 on the set with a gradient that goes to 0, and fix our harmonic L2 object, small s, and 1 arbitrarily set in the exhaustion. Okay, we have this series of equality and inequality. Okay, since our object is harmonic, this product of course gives 0. Then we can think to multiply by the cutoff and take the limit. The equality will be clearly satisfied. After that, we apply Weizsäck formula to this Laplacian. And then we can think to, in this term, to integrate by parts, and we appear, and the gradient, a norm of the gradient appear. Okay, this one is not modified. Okay, is exactly I just rephrase this one. Okay, now the trick is to split this first integral into two parts. See what happens in the fixed set vk, and see what happens in the complement. If since k is fixed, when we take n big enough, here the Φn is equal to 1. Okay, so that's the reason why here we see phi n, here we see just s. Okay, now, so far there are more or less trivial computation, standard, not trivial, but standard, very standard computation. Now the main tool of this proof is the refined Kato inequality. So Kato inequality, how to say, the classical Kato inequality is like this. Huh? So we have that the norm of the gradient can be estimated by the gradient of the norm. Okay, and this is very general, but resolved by Kaderberg, Duchon, Herzlich says that if the object S is harmonic, exactly as in our case, we can improve a little bit. Okay, there is this strictly positive constant, which may depend on the set, but we don't care, such that the Kato inequality is improved. Okay, we have this extra term because of harmonicity. Okay, now the idea is to use here the classical, we can use here classical Kato, and here, since here we have S is harmonic, we have the refined. Okay. Okay, let's do it. And so we get this expression. No? The last addendum never change. Okay. Now the idea is that this one, the fact, this green factor can be merged here. Okay. And in this way, we have an integral over n of the gradient of the norm, plus, but now we have this reminder. Okay, we have this extra term, and then we can apply a trivial step. I can add and subtract this term here. Okay, and finally, I rearrange in this way all the addendum, and we have that each addendum has a sign. The first two by hypothesis, because they was exactly the hypothesis of our theorem, and this one is trivial, and the last one is trivially satisfied. So the conclusion is that since each one of the three terms has to be 0, in particular this one has to be 0, which means that the norm of S is constant, which is exactly our conclusion. Okay. Question? Now, in the rest of the talk, I would like to apply this theorem that I just proved in some setting, trying proving some vanishing theorem for stable minimal surfaces. Every time we will have some suitable positive curvature hypothesis. In each application, different curvature hypothesis on the ambient manifold, but every time it is positive, the curvature of the ambient space will be positive in suitable sense. The first sense is the following. We have the curvature operator. So given a Riemannian manifold, the curvature operator is something that acts on B vectors, and it seems by definition just a rephrase of the usual Riemannian tensor, but they are not completely equivalent in the sense that if the curvature tensor, sorry, the curvature operator becomes a symmetric bilinear form on two vectors. So we can think about its eigenvalues, eigenvectors, and so if, as usual, if all the eigenvalues are strictly positive, we say that the operator is strictly positive. So if the curvature operator is strictly positive, of course, the sectional curvature is strictly positive, but it's not the opposite in general is not true. So the most famous example is the compressed projective space with the Fubini study metric. It's well known that here the curvature is between the sectional curvature between 1 and 4, but the curvature operator has some zero eigenvalue. Okay. Okay. Now examples of Riemannian manifold with non-negative curvature operator. There exist a lot. The Euclidean space, sphere, complex quaternion projective spaces, of course. If you want some more exotic example, we can take Berger spheres. So we are deforming by parameter delta the usual round metric, and one can compute the curvature operator of such a new metric, and if delta is smaller than this quantity, the curvature operator is strictly positive. Okay, and of course, also the product of two or more manifold with non-negative curvature operator are again a manifold with non-negative curvature operator. Okay, now after this introduction about the curvature operator, it's time to give a first application of our general result to stable minima hypersurfaces. So we are in a Riemannian manifold with dimension big enough and a non-negative curvature operator. So we pick any integer between 1 and n minus 1, and let M be a complete orientable stable minimal hypersurface of this ambient manifold. Suppose that the following condition about the principal curvature holds for any multi-index alpha of order P. So here we have the sum of the lambda I square, every one appears, every principal curvature appears here, but here they appears just a selection of P principal curvature. We take the sum and then square of the sum. Okay, I'll comment in a moment this condition. Okay, but our hypothesis is that exactly that for any multi-index alpha, this quantity is non-negative. Then we have exactly the same conclusion of tan. So every harmonic L2 P form omega has constant length, and the volume, if the volume of the minimal hypersurface is plus infinite, this harmonic object is trivial. Okay, so in the case of tan, we don't see this because we know that minimal hypersurface in the Euclidean space have for sure infinite volume, okay? And that's the reason why in Tanno we go directly to this conclusion. But in general, since here we don't know, in principle it could be compact. We have also this first statement, okay? So some comments about the hypothesis. So this condition is about the second fundamental form, is automatically satisfied in some cases. When P is equal to 1, it becomes quite evident because here we have just one addendum, and so it's quite evident. But also, is for sure satisfied for n equal to 4, for any P in that case, okay? Any P, but n equal to 4. The proof of this fact is again the nice paper by Tanno, and reading his paper, our idea is that he decided to take to work in a Euclidean space of dimension small enough exactly for this, to not write in a condition like this, hoping to generalize as much as possible. We decide to introduce it. Okay. Moreover, it's of course it's not it's a quite we don't know, to be honest, at the moment we don't know how strong is this condition, but for sure it's not, it doesn't make the problem trivial, in the sense that after this condition it's not automatically true that the second fundamental form is 0, or that the second fundamental form is bounded, for example, because if you have from at least algebraic point of view n like this, the sum of the lambda is 0, and it's easy to check that this one satisfies this hypothesis for any n, for any p, for any alpha, and for any value. Okay. So the problem, so of course, is a new hypothesis, but does not trivialize the problem. Okay, since by this remark, since this hypothesis automatically satisfied when n is equal to 4, n is, I recall, is the dimension of the hypersurface. So it could be interesting to see what happens in some famous 5-dimensional Riemannian manifold. Okay, so for example, round sphere, or the product S2 cross SR, the sectional curvature is not negative, but the Ricci is strictly positive. So by the result by Catino, Mastroianni, and Coroni that I mentioned some minutes ago, those spaces have no stable minimal hypersurface at all, compact or non-compact. Okay, then we can try to take product like this, B cross R, where B is the four-dimensional, of course. It can be, for example, the round sphere, the product of 2 round spheres, the complex projective space. Then, by the curvature hypothesis of this space, again, the result by the same authors, Italian authors, Catino, Mastroianni, and Coroni, says that stable minima hypersurfaces in those ambient spaces are compact. And then using compactness, as we did at the beginning, we have a very precise picture of stable minimal hypersurfaces in space like this. They are totally geodesic, with Ricci on the normal equal to 0. So for sure they are the base times at naught. And if we take other 5-dimensional famous examples, such as S3 cross R, S2 cross R3, they don't satisfy the hypothesis of Catino, Mastroianni, and Coroni. So our result, our theorem B, is new. In dimension 6, we have we can also Catino Matrostrillero colony result apply, so we can have a situation like this. So in some cases no existence, in some cases trivial, in some cases new result. But of course we have to add this hypothesis because this one is no more necessarily satisfied. And in dimension bigger than 7, as far as I know, everything is new. Okay, even in the 7-dimensional analogous of those spaces. Okay, why? Let's give a very short a sketch of the proof for theorem B. We want to apply theorem A with Q, this quantity, the normal second fundamental form plus the Ricci, and L, since we are considering P form, L has some special name, is the Bochner operator, and could be complicated to write, but it's quite understood. So let's see if delta minus Q is non-negative by the stability. So this one was one of the two hypotheses of the theorem A. Moreover, Bochner applied to a form omega is a non-trivial combination of the Riemannian curvature of the hypersurface with the form. So using Gauss equation, we can split as usual the Riemannian curvature of the hypersurface as some term which depends on the curvature of the ambient, some terms that depends on the second fundamental form. So this splitting pass to Bochner operator, and so the Bochner operator can be split into Px and Prs, where Px depends on the second fundamental form on A, and this one depends on the Riemannian curvature of the ambient manifold. So a big help arrives from a paper by Alessandro Savo, who estimates the two terms separately. So Bx can be written like this: is the minimum of the multi-index of order P of the sum of the principal curvature with index in alpha times the sum of the principal curvature with index not in alpha. But since now our M is minimal, the sum of the principal curvature is 0, so this term is the opposite of this one, and so we can rewrite like this. Moreover, again Savo in the same paper proved that if the curvature operator of the ambient manifold is bounded by C, a constant C, in our case it will be 0, this constant will be 0, Bres is bounded by P dimension minus P and C times the constant. So in our cases, now take C equal to 0 in our case. Okay, so this one becomes non-negative. Again, three standard things about the curvature operator say that if the curvature operator, as in our hypothesis, is non-negative, then the Ricci is non-negative too. And so it follows that also this term has a sign. The two hypotheses of theorem 1 were this element has a sign and this element has a sign. Okay, so we have done, we can apply our theorem A, and so we have the conclusion. So the harmonic object, in this case, the integrable P form, has constant length, and if the volume is infinite, this one is trivial. Okay, I would like to discuss very briefly another application. This one, as far as I know, is completely new. And concern harmonic spinors. So of course, I unfortunately don't have time to introduce very precisely, but a spin group is the twofold covering of the special orthogonal group, and the Riemannian spin manifold is a Riemannian manifold with a fixed spin structure. So a general fact is that the existence of such a structure is just a topological question, okay? Maybe, and if it exists, it's not unique, okay? Now, with Francesco Bay, we had this spinorial version Tanno problem. So we have, if the ambient manifold has a scalar curvature non-negative, and we take a complete oriented stable minimal surface, fix any Riemannian spin structure on M, and take an harmonic L2 spinor, then the conclusion are always the same. This harmonic object at constant length, if the volume is finite, this harmonic spinor has to be trivial. Very quickly, the proof was again an application, the direct application of theorem A with the right ingredients. And so Q this time is this, and L is 1/4 the scalar curvature of the hypersurface, because we have this well-known Rilke-Rovitz formula, which related the square of the Dirac spinorial Dirac to the scalar curvature. And again, similarly to the previous case, we have that our hypotheses are satisfied. This one, the first one, again by stability. Then once again, we can apply Gauss equation to write the scalar curvature of the hypersurface as the scalar curvature of the ambient manifold plus some remainder. And then after some standard computation, one can prove that L plus Q is non-negative. Okay, so the theorem, the hypothesis of theorem A are satisfied. And in just 1 minute, I would like to conclude talking about stable CMC hypersurfaces. So CMC stands for constant mean curvature hypersurface. So also for this kind of hypersurface, that's a notion of stability. Indeed, there are two, sometimes called strong and weak. Here we are considering the strongest one, which essentially is the same. The difference with the usual stability, or sometimes called weak stability for CMC, is that here we are not requiring that the test function has integral 0 over the M. Okay, so the nature of the operator of the condition is the same as a stable minimal hypersurface. So theorem A can be applied also in this context, and so very briefly, we have the analogous of theorem B for CMC, where now the hypersurface has constant mean curvature H, and everything works exactly in the same way as the theorem B for minimal, except that the H appears in this condition. And again, also we have the spinorial version. Here, the different also H appears in the hypothesis in this case, and in particular, we can relax a little bit the hypothesis about the scalar curvature ambient. Here, if you allow a strictly positive H, then the scalar curvature of the ambient manifold could be negative, but not so negative. So this sum has to be non-negative. And then the conclusion, we arrived to the same conclusion, the vanishing of harmonic L2 spinors. And with this, I am really done. Thanks for the attention.
Thank you. So are there questions or comments? Okay, so are there question or comment from Zoom?
Yes, I have a question. Can you hear me?
Yes, please.
By spinorial tunnel result.
Wait, repeat, please. Repeat.
Yeah, this
Spinorial
one.
tunnel.
Can you say something about topology on a stable minimal hypersurface? So,
Repeat, please.
By spinorial tunnel result,
Yes.
can you obtain some topological conclusion by the
Yes,
vanishing
yes,
of
of course, yes. No, the space of harmonic integrable spinors has some topological interpretation. It's called A hat genus. No? It implies that the A hat genus is zero, which is the vanishing of some cohomological classes, but there's no, at least for my knowledge, there's no an evident geometric conclusion. For vanishing of one form, you have this very, from my point of view, unstable consequences. The number of ends of you can count the number of ends of the minimal hypersurface. Now, this is of course a topological object. Okay.
Yeah. Okay, thank you. And I have one more question. Okay.
Yes, please.
I'm interested in your hypothesis about second fundamental form A.
Yes.
Do you have any non-trivial example satisfying that hypothesis?
Okay.
This condition.
Okay. Of course, this one is algebraic.
Yeah.
An algebraic example. Then, if there is a hypersurface with exactly this second fundamental form, no, it's another factor. Okay. So one. Thanks for the question, because yes, we have, but not for any P. Depends for P small. For example, the Bombieri, De Giorgi, Giusti examples are in complete graph in R2M plus 1 with M bigger or equal than 4. Okay. And so those examples has some symmetries, even if it's hard to compute explicitly the principal curvature. You can by symmetries you can say that M, there are lambda 1 equal to lambda n equal to lambda m, and then we have lambda n plus 1 equal and so on. Okay, there are two types. Principal curvature have a lot of multiplicity, and so you can see by hand that this condition, even you don't know explicitly the value, since they have a lot of multiplicity, you can see that this condition is true for P small. For example, in the easy case, when M is equal to 4, this one is true. In the example Bombieri De Giorgi Giusti for P equal to 2. And of course, by duality, P equal to 8 minus 2, which is 6. Okay. So but of course it's not for any P.
Yeah, okay, thank you very much. So do you believe so can you remove this hypothesis on A?
With
maybe difficult.
No, it's difficult. Of course, it will be great to remove it, but you need very different arguments.
Yeah.
This one appears from the where is it? this thing by Savo, okay?
Yeah. Okay.
Because Savo compute explicitly this one, but of course here we are doing a previous step. We are splitting the Bochner operator, okay? The splitting makes each addendum much easier, but probably in the splitting we are losing something.
Yeah, I understand. Okay. Yeah, but it would be great if you remove the condition.
Yes. If you have some ideas, please do it.
No, I have no idea, but I have same problem, a very similar problem. So I was interested in your hypothesis. Yeah, but anyway, yeah, it was very interesting talk. Thank you very much.
Thank you.
Is it okay? So the the other question or comments? As a comment from Zoom or in the room? Okay. Sorry, I have some questions for you. And you said A hat genus is the topological invariant of the. But
Yes.
M is a complete, not compact manifold. So can you define the A hat genus on the complete manifold? It's a topological invariant? L2 sense or some L2 sense? A hat genus.
Okay, to be honest, is my collaborator who know very well spinors, okay? So I'm not I'm new in spinors, so I don't know exactly the answer. So yes, of course, not non-compact example are more delicate, but I don't know. To be honest, I don't know the precise answer to your questions. I'm sorry.
Okay, so I have another question of your theorem A. Can you show me the slide of theorem A?
Yes, of course.
So in the theorem A, in the proof of the theorem A, you are main theory. This means cut-in inequality, defined cut-in inequality. I think they discussed the more general setting. I mean the Calder Bank Gaussian Hertzrich in their paper, they discussed the more defined cut-in inequality, more general setting, not only the Dirac operator, but also some Stein-Weiss operator, some the general gradient Stein-Weiss operator. So my question is that so you can generalize your theorem A for the other, I mean some geometric first order differential operator.
Thank you. No, okay. In the paper, we also consider not only Dirac operator but Schrödinger operator too. But I prefer to in this talk to talk about just Dirac operator because it seems to me more easy to explain. Okay.
Yes. Okay. I see.
But thank you.
Yeah. Okay, thank you. So are there questions or? Okay, so let's thank the speaker again.
Thank you.